Okay, welcome back. This is session C. Our first speaker is Michael Beverland. He's going to tell us about the cost of universality, a comparative study about the overhead for magic state distillation. This is joint work with Alex Kubica. Thanks very much, Michael, for joining. And you have 25 minutes plus 5 minutes for questions. And at the end of the session, we're going to have, you're welcome to type your questions into the Slack channel. At the end, we're going to have a roundtable discussion with each of the authors where you can ask more questions there as well. So take it from there, Michael.
Cool, thanks a lot, Steve. Let me make sure first that this is working. You can do a thumbs up. Okay, well, I'll infer it was. It's really nice to be able to speak at QIP about this work. This is a project that I'm very proud of, something I've been working with Aleksander, Kubica, and Krysta Svore on for a number of years. We posted it to the archive last month. The posting is below. And it's really a project that ties together a number of different areas of quantum error correction and fault tolerance and answers what I think is an important, or it addresses what I think is an important question. And that question specifically is, what is the best approach to produce a universal set of fault-tolerant gates in realistic settings for quantum computing? And what we do in this project is we compare two of the main ideas for this, at least as I see it. So the first is state distillation, and that can be crucially implemented in two-dimensional code, such as the surface code. And that's really what we should think of as the status quo. That's the standard approach. And that is, that's something that is known, it's understood quite well, and it's known to be expensive and often represents a large fraction of the footprint whenever you lay out a full algorithm and imagine how it would be really laid out and implemented on a fault-tolerant quantum computer. So that's the baseline, and that's something that's we would really like to reduce the cost of. We would like to replace that with something else, if possible, that's better or more inexpensive. And the approach that we're comparing that with is a newer idea by which was introduced by Hector Bombin, and that is to use something known as code switching to a three-dimensional code. And the fact that it's three-dimensional is really something that we should pay attention to. 2D, if you ask any experimental friends, or if you're an experimentalist yourself, most architectures, most approaches to build quantum hardware would be much easier in 2 dimensions than in 3 dimensions. So if we are going to suggest moving to 3 dimensions to avoid state distillation, then we would really hope that code switching would be something which is much preferred, much cheaper, requires far fewer qubits. So in this project, we're really looking at the overhead of these two approaches. And just as a guide for the talk, we're going to start by specifying the assumptions that we make. Then we are going to briefly review 2D hardware and what can be done there. Then we're going to talk about how in 2 dimensions, non-Clifford gates can be implemented through magic state distillation. Then we will cover code switching, which is the approach that requires 3 dimensions. And then finally, we will conclude and show results. Okay, so the setting that I want us to imagine is a very standard one. It's what we often consider in the field of quantum error correction, where we imagine, for example, a 2D grid of qubits, and the quantum operations that are allowed are local. So we either have single qubit in this project, we either have single qubit operations, preparations, measurements, unitaries, etc., or we can couple together pairs of qubits, but through, for example, a CNOT gate or a measurement of a pair of Pauli's or something like that, but they have to be nearby to one another. And then the noise that we assume in this project is the standard circuit noise model. So the idea there is that every operation, every quantum operation can fail with some probability p. So suppose that you wanted to produce, for example, a qubit in the 0 state, then with probability p, it actually gets prepared in the plus state. That's the noise model that we use. Similarly, if you have a CNOT gate, then with probability p, that will actually fail, and we'll have a random Pauli operator applied to its support. So that's the allowed operations and the noise in 2 dimensions, and 3D is exactly what you would expect. It's just the analog, but where we move to a 3D grid rather than 2 dimensions. So what does 2D allow us? What can we actually achieve? Well, we can do a lot, as we know. We can build particular surface codes. So we can tile the plane here with these colored squares just to guide the eye, and break up that tiling into these smaller patches. So each of these patches is a distance 5 surface code and stores a logical qubit. And that's one approach. I'm not going to focus on surface codes in this talk. I'm going to focus on a close cousin, which is the color code, which is very similar. In this case, we tile instead of with squares with hexagons, and again break down that tiling into smaller pieces, and each of these smaller pieces here represents a distance 5 color code. So the key property here, or a crucial thing for protecting information in a quantum computer, is that we can scale the size of these patches, which we can refer to as the code distance, and we can scale the length of these patches so that the error is suppressed in the logical information that's encoded, provided that the physical error rate is below the threshold value. And crucially for color codes and surface codes that you can implement in 2 dimensions, these thresholds can be quite high, on the order of 1%. Something else that you can do in the color code, which is very beneficial, is that you can implement the full Clifford group transversely. And this is important because these gates, where you implement them transversely, by which I mean each qubit in the lattice is addressed separately and individually. So to implement a Hadamard, we apply Hadamard to all the data qubits in this little patch, and that's automatically fault tolerant, simply because a problem, some error in some region of the lattice, will not propagate to other parts of the lattice because each qubit is being addressed separately. And it's very important that you can, or it's very useful that you can implement the full Clifford group here. Another thing that you can do is you can couple together logical qubits stored in adjacent patches, so patches which share an edge, and you can use the technique known as lattice surgery to implement a logical joint Pauli measurement between those patches. And this allows you to achieve all so the combination of these single qubit Cliffords and these Pauli measurements, and also fault-tolerant preparation of basis states and measurements of individual qubits, that generates the entire set of Clifford operations in 2D. So we got very far with 2 dimensions. We can implement all the Clifford operations in a protected way. What about non-Clifford gates? We know that we need something beyond Clifford operations in order to achieve a universal quantum computer. Well, one thing that you might hope for, at least initially, is that there's some transverse gate that we were missing. Maybe there was some other non-Clifford gate that was transverse and we just hadn't found it yet. This had been ruled out by Bravi and Koenig, and unfortunately, there's no approach like that. However, there are a number of other approaches that are known and have been known for some time in the field of quantum error correction to achieve some non-Clifford gate. One approach, which was used in the early fault tolerance papers, can be known as the cat state method. And that involves essentially preparing a cat state on a small number of qubits. And this is useful if you're in the setting of concatenated codes. Another approach that we've already mentioned is state distillation, which I'll come back to later. And then, of course, we have a number of ideas which came much later than the other two, but which are much less well understood. And so importantly, in 2 dimensions, for whenever you want to use a topological code, so a code like the surface code or the color code, and you want to do this at scale, then in 2 dimensions, the only approach that's known to be applicable is that of state distillation. So how does state distillation work? Well, it's built up in a number of steps as shown here. The first step is actually a non-fault tolerant step, so a noisy step. And in that step, we produce a state which is not a basis state, but a magic state, it's known. So something that cannot be produced by Clifford operations. We produce that in a 2D color code, a small 2D color code. And because this is an unprotected procedure, that part is noisy. The next step then is we take that noisy small 2D color code and we expand it and make it into a larger 2D color code. And this at first seems like a strange thing to do because now we have used a large number of qubits to make this big 2D color code patch, but we're only encoding something of very low fidelity. And the reason that we do that is because the next step is to run a distillation circuit, which is a Clifford circuit. So this can be run with the operations that I described above in this 2D arrangement. And this protects against noise because everything is done in a fault-tolerant way. And the effect of this distillation circuit is to take a number of copies of these noisy magic state inputs and to produce a smaller number of copies of much lower noise outputs. And this might achieve some accuracy after one run of this distillation circuit. And if that's not enough, then you can just repeat steps 2 and 3 again, i.e. enlarge the output and rerun distillation on this bigger 2D color code until you achieve the desired accuracy. And then finally, the last step is to inject this state. So to convert essentially this state that you've produced into a gate. So here we show this gadget. Again, this is a Clifford gadget. So all of the operations are protected and any input state can be used. And the effect of this is to apply a T-gate, a non-Clifford T-gate to that state. So it might not be too surprising that this is costly because of this iteration that I mentioned before. The idea is that in each round of distillation, the number of outputs is less than the number of inputs. And so we end up with this tree-like structure. So there are a large number of inputs required for distillation. And so that can lead to high cost. Another way of thinking about it is that the circuit that I mentioned, this Clifford circuit that's run with 2D color codes, is itself potentially quite hefty. Here is an example of a laid out distillation circuit. And remember that each of these wires, because this distillation circuit is running at the logical level, each of these wires represents a 2D color code, not a single qubit. And each of these operations is a logical operation. So in order to implement one logical T-gate, we really need a lot of logical Clifford gates. And so this is another intuition behind why this is such a costly piece of quantum computing. It's useful to get some insight by looking at the asymptotic behavior in the limit of low output infidelity of the magic state. So when we look for really, really good quality magic states, what happens? And here, we're characterizing distillation in terms of a few parameters, a pair of parameters. We take, for each output state in distillation, we use R inputs, and the order of error suppression is F. So quality Q, infidelity Q of inputs becomes an infidelity proportional to Q to the power of F. And so we can count up the number of copies in each round. And this is straightforward. The last round requires R copies of the T state to be put in because it's an R to 1 scheme. The round before that would require R squared inputs simply because each of the R inputs in the last round needs R inputs of its own, etc. And so the first round, when there are n rounds in total, requires R to the n copies. And it's relatively straightforward and well known, the scaling of R to the n, the scaling of the number of copies needed in the first round. And the way that that behaves in the limit of low Q out here, which is the final output T state infidelity, is log 1 over Q out to some power, where that power depends only on these parameters that I mentioned before of the distillation scheme. However, there's another thing that we haven't yet discussed, which is the fact that the code distance is increasing throughout the protocol. And as we described before, the reason for this is each time you run a distillation round, the output is better than it was before. And so you're going to need a bigger code in order to protect it. And so this kind of counteracts the effect of the number of rounds, which is going down, or sorry, the number of copies, which is going down as you increase the round number. And so question is, what is the overhead then of the most expensive round in terms of the distance, which will be dominated by the last round? And that actually has a similar behavior to the r to the n, in that you have log 1 over q to some power, but now the power is fixed to the number 2. And of course, the total overhead is the product of these two things. It's the number of copies times the number of qubits required for each copy. And there's a trade-off between these two things. So if you have gamma, which is below 2, then actually the final round will dominate rather than the first round, which is something that I don't think people have thought about very much. There's a lot of focus has been put on in the distillation literature on getting lower and lower gammas, but this analysis indicates that maybe actually we should be focusing on slightly different things, because if you take gamma below 2, then the cost of distillation is no longer dominated by the first round anyway. So that's a little bit of an aside, but I think it's an interesting thing that we found along the way in this project. Okay, so going beyond this asymptotic analysis, we did numerical simulations, full numerical simulations of distillation. And this, I'm going to flash a couple of bullet points here, but each bullet point actually represents months of work. So the first thing that we did was implemented a simulation of the two-dimensional color code and optimized the stabilizer extraction circuit, so the precise details of how the syndrome is read out from the 2D color code, and also developed the fault-tolerant decoder, which was essentially an extension of Delphos's projection decoder. Another thing that we then did was analyze the logical failure modes in 2D color codes, and this allowed us to simulate logical circuits like the 15-to-1 distillation circuit. And then once we had that infrastructure, we were able to simply specify a distillation scheme, so a set of distances for a particular number of rounds of distillation, and then find what the output error rate of the final magic state would be, and then just minimize, by searching over various distances, minimize the cost required. And so, unsurprisingly, the behavior of that cost is that it grows whenever you want more accurate magic states. And also it grows whenever you use more faulty hardware, so when you increase the underlying error rate. And these numbers are very large. Unsurprisingly, we were doing this based on the 2D color code, which has slightly worse circuit performance than the surface code, so the numbers are even larger than for the surface code. But in either case, it's clear that distillation is expensive, and we needed a benchmark with the same code that we're going to use for code switching in order to make a direct comparison. Okay, so what about 3 dimensions? I mentioned before that we could benefit from 3D, so how does that work? Well, although the case was that in 2D, the state distillation was the only horse in the race, whenever we include 3 dimensions, so whenever we allow for 3-dimensional operations, then another trick that can be used to achieve non-Clifford gates is code switching. So this is a very high-level sketch of how 3-dimensional color codes work. But the idea here is essentially that in 3D, we will use, we will be able to build a 3D color code, which unlike its 2D, the 2D member of the color code family can actually host a logical non-Clifford gate. And in the 3D color code, the stabilizers can be thought of as having two types, X type on little volumes within the lattice and Z type on little faces within the lattice. But crucially, as I mentioned, the T gate is transverse in this code. In the case of so there's another example of 3D color code, which is the subsystem version, which looks like, here's a schematic picture of it. And for those of you familiar with subsystem codes, the gauge group is defined in terms of these X and Z operators on faces, and the stabilizer group is defined in terms of X on volumes and Z on volumes. So this is symmetric now between X and Z. And notice, importantly, that the X part of the stabilizer group of the subsystem code is the same as for the stabilizer version of the color code. And in fact, any state of the 3D stabilizer color code is automatically a state of the 3D subsystem code. So if you prepare the stabilizer code, then you're in a particular state of the subsystem code. And a way that you can move back, you can move from the 3D subsystem code to the stabilizer code, is simply by measuring the stabilizers, the Z faces, which were our stabilizers in the stabilizer code, but not in the subsystem code. And when you do that, you might get some random outcomes, which is what these loops represent, but you can fix them by applying some appropriate operator. Another very interesting fixing of this gauge, so fixing of the subsystem gauge, is shown on the right. This was found by Hector Bombin. And the idea here, it's kind of remarkable. You can choose another set of, you can choose another particular choice of the gauge qubit states of the subsystem code, and you end up with actually the 2D stabilizer code and some bulk, which is in some trivial state. And again, because this is a fixing of the gauge, that if you're in that state, then you're automatically in the subsystem code. Okay, so we can use this to implement code switching and to produce a high fidelity T state in the 3D or in the 2D color code. So the idea is we're going to start in 2D and end up in 2D. We're going to go into 3D in the middle to implement the T gate. So in particular, the approach that we analyze is as follows. We start by preparing a Bell state in a pair of 2D color codes, and then we will ignore one of the pair until later. But the second of the two 2D color codes is then put up against a 3D bulk that we can prepare. And this is now the second gauge fixing of the subsystem color code that I mentioned before. So this is actually in the subsystem color code. And our goal is going to be to put it into the other stabilizer code. So we measure the Z faces, as I mentioned earlier, and that will produce these gauge terms, which we need to fix in order to end up in the stabilizer code. When that is done, there's going to be some residual noise, of course. The gauge will not be fixed perfectly, but now we are almost entirely in the stabilizer code where the T gate is transverse. So we can apply the T gate transversely and then measure out all of the qubits in this 3D code. And then we go back to our other half of our Bell pair where the T gate has been teleported to. And we may require a fix operation to put the T state into its proper place to correct it. Okay, so there's not a lot of time to go into details, but the main idea here is that we really implemented every step of the procedure that I showed before, and we did so in a relatively careful way. So we went through each of the the steps and tried to make sure that each of the preparations and the gauge measurements were implemented in as low depth as possible. We also found efficient classical decoders for fixing the gauge and also for the final step where we needed to perform error correction for the 3D color code. And this produced the plot that I show you here for a variety of distances. We can just check what the probability of code switching the whole protocol failing is. And you can have a relatively simple fit to this data, and that can be inverted to give you an overhead. So it can tell you in particular what distance you would need to achieve a particular desired output infidelity. Hi, Steve. I almost heard you there. Is that a time warning?
Yeah, I'm doing the annoying thing where the chair stands up next to you and
well, how much time do I have?
Looks at you and says, "Yeah, are you going to wrap up soon?" So
okay,
that's what I'm doing.
Thanks, Steve. That was very verbose way of saying it too, using all my time. The other thing that we do here in this, which I think is quite useful and it gives us many insights, is we bound the potential impact of improvements on each step in code switching. So in particular, we how long do I have, Steve? Like 1 minute, 2 minutes?
You have 4 minutes. You're going into your question time right now.
So. Okay, that's fine. Okay, so for each step, we try something which would be, we replace that step by something which would be optimal. So for example, when we prepare the interior, we replace that, which we have a way of preparing the interior that we know exactly how to implement. We replace that by a perfect preparation, which then involves just 3 time units of single qubit errors, which is the minimal amount of time that would be required to do the preparation. We don't know any way of actually achieving that performance, but it gives us a bound on how good you might hope to be able to get by doing that better. And we do that for all of the steps. And so the main results are that code switching performs worse than state distillation, unfortunately, in the most reasonable setting of physical error rate, 10 to the -3 that we study. And it's important to consider here in these curves the blue line and the green line. So the blue line is our simulation of code switching, and the green line is our simulation of state distillation. And so in the first setting of the underlying error rate P, we can't see the blue, and that's actually because we are below the threshold that we found for code switching. So code switching won't work at all there. It comes a little bit closer to distillation in this value, and then it really does actually kind of bump up against distillation and start to slightly outperform it in some settings for much lower physical error rate. But it's still quite far from being as much better than it as we would want it to be in order to merit going to 3 dimensions. I am going to stop, so I will leave with my final slide, which is that code switching is not substantially cheaper than state distillation in the error rates that we looked at, which are the physically motivated ones, and that this also is true even if we replace all of the steps by highly optimistic improvements that are unlikely to ever be realized. Okay, so you can ask questions in the after session. Thanks,
you can
everybody.
ask questions now. If somebody has a question, so there haven't been questions posted to Slack.
Okay.
I have a question.
Sure.
And you have 1 minute to answer. What's the bottleneck in code switching? Like if I wanted to improve it, where's the bottleneck?
So yeah, that's one of the things that was nice about this approach of checking all of the things that we could improve. So none of the things are going to improve you that much, right? But the thing that would improve you most is having a better decoder for the 3D color code. So this bottom line, these bottom lines, these orange curves here, that involved us using an optimal decoder. So we know how the optimal decoder performs with the 3D color code. So we used an optimal decoder in the simulation there, and optimal everything else.
I see.
That's kind of the best you could possibly do.
Thanks. So, okay, for other people, there's at least 2 questions now in the Slack channel. So Michael, you're welcome to go answer them there. Also, at the end
Cool.
of the session, we're going to post links to 3 separate, I forget what we're calling them, breakout roundtables, where you can talk to the individual speakers about their specific talks and ask them any questions that you like.